So we're going to go. So we look at a few different examples, right, dealing with theoretical, right? So the kind of the last thing we left off was, right, theoretical versus experimental probability. And there was a lot of examples that I can ask, right? So we looked at just calculating theoretical and experimental probability. That was your, right, what mainly your AC was on yesterday. Then we looked at, right, we can use experimental probability to make predictions when we're only given experimental probability, but when we're given both, right, we always want to use the theoretical probability, right, when we're given both to make predictions. So we went through a few examples there. And then we looked at, again, some different questions looking at, right, theoretical and experimental probability, right? So again, I just kind of want to reiterate when we're doing these questions, right? So for example, on your AC, I always kind of write down what, right? So we're given the spinner that's being spun, and we're given the table that of the results that when Bradley spun the spinner 40 times, right? So what I always do is write experimental under the table. So, right, any questions that ask for experimental probability, I know right away I'm just looking at this table here, and I'm not looking at the spinner. Right, and vice versa. Any questions that are asking about theoretical probability, I'm looking at the spinner, and I don't worry about what Bradley got in his results. Right, and then you also had a question on your AC about sample size, right? So effects of sample size on results. So again, these questions are just kind of, right? The gist of these questions are a larger sample size means that we will get a more accurate probability, right? A larger sample size means our experimental probability will be closer to what we should get in theory, which is what we want, right? So for these questions, right, it's asking, right, if 10 people don't order a certain dish, does it make sense to just take it off? Well, no, because you still have 390 people that could possibly order that dish. So again, just different questions I can ask about sample size, right? But again, the main thing is that a larger sample size means a more accurate probability. And then finally, we looked at, right, the last thing we looked at was probabilities involving outcome tables and tree diagrams. So up to this point, we right, so up to this point in the book, we were dealing with scenarios where we were only looking at one event. So, right, what's the probability, right, when we're drawing decks of cards? What's the probability when we're rolling a die? But now we can look at, right, the possibility when two separate events are happening. Right, so in this case, our first example we looked at was, right, we have two choices of a meal and three choices of a drink. How many possible combinations of different orders can we choose? And for these type of diagrams, or for these types of questions, we have two diagrams that we can make to help us figure out how many possible outcomes there are. Right, so first off, we have this formula here, right, where the total number of outcomes equals the number of options in event 1 times the number of options in event 2 times the number of options in event 3, and so on, right? So for this one here, we had 2 options for meals, so it's 2, and then we had 3 options for drinks, so 3, so 2 times 3 gave us 6 possibilities or outcomes. And right, another word for this is we call this our sample space. But to see what these different combinations of outcomes are, we can use a tree diagram, which looks like this, and a we call an outcome table, right, where we have one outcome or one event for rows and one event for the columns. So let's do, and we did one example on Monday. We're going to do look at another example. So we did this example looking at a four-sided die being tossed during a game. We're going to look at page 41 here. So another example. In this case, we have a game consists of tossing a coin and spinning a spinner, right? So we have two different events here. We're tossing a coin and spinning a spinner. So how many possible outcomes are there? So I'm going to say, if I use that formula on the previous page, right? So let's say this is event 1, and then spinning the spinner is event 2. So how many possible outcomes do we have for tossing a coin? 2. We can either get heads or tails. How many possible outcomes do we have for spinning the spinner? 5. Yeah, there's 5 spaces. So there's 10 possible outcomes. And now we want to make an outcome table and a tree diagram showing, right, the different combinations of these outcomes. So I'm going to put coin toss, right? So it can either be heads or tails. And then for my rows, it's going to be the spinner. Right, so the results that I spun. And that could either be green, yellow, purple, red, or blue. Right, and now it's just a matter of, right, lining those up. So we can spin green and toss a head, or we can spin green and land on tails. Right, we can have yellow and heads or yellow and tails, purple and heads or purple and tails, red and heads and red and tails, or blue and heads and blue and tails. Right, so we have 10 possible outcomes, and this is what they are. Right, this table shows us the different combinations of what we can get. If we want to do the same thing, but a tree diagram, using a tree diagram, right? So yours may look a little different. So, right, you can either split it up into the coin tosses first, or you can split it up into the spinner first. Either or doesn't matter. I'm going to do let's do the spinner first, right? So we have green. So there's 5 possible outcomes for the spinner, right? So we have green, yellow, blue, red, and purple. I missed purple. Okay. Right. So again, you could have split the tree up into heads or tails first. Doesn't matter. Yeah. Sorry. 36. This one here. right? So you could have split it up into tails and heads first. Doesn't matter, you still end up with the same results, right? So now you can split up each color into, right, heads or tails, right? So we have heads or tails, heads or tails. And then we have our outcomes here, right? So we have green and heads, green and tails. Right, and we do that for each. We just follow along the tree, right? So we have red heads, red tails, and then for purple, right? So a total of 10. They both two different ways of getting the same, of displaying the same info. So based on looking at how your AC went, probabilities, I think we're pretty good on, right? Just remembering when we have a question dealing with asking for theoretical and experimental probabilities, just knowing what information to look at. But I think a lot of people are still struggling with odds, right? So don't forget about odds. So for part C, what is the probability of the outcome, including the spinner, landing on purple? So what is the probability of the outcome, including the spinner, landing on purple? So probability of, I'll say, well, I'll say outcome includes purple. Right, so it's worded a little weird. What is the probability of the outcome, including the spinner landing on purple? Right, so we're looking at this branch here, or in this case, this row here. So how many outcomes out of the 10 include the spinner landing on purple? Yeah, 2. Thank you, JC. There's 2, right? Right? You can purple in heads, purple in tails, right? Looking at this row here in the table, or looking at these branches here in the tree, right? And there's 10 possible outcomes, right? And if we wanted to convert this to decimal and percent, it's 0.2 or 20%. Now for the odds, right? So we have the probability. Now we want the odds of outcome includes purple, right? So we have the odds is, right? Outcome includes purple. So in favor of including purple and not include purple. So again, you don't have, I'm just writing this for your notes. Because again, looking at, based off the AC, we still need to work on, right, stating odds. Right, so we want the odds of including purple. So that's the first number we put in our odds. So how many ways can we land on purple? Right, JC said 2. or our outcome includes purple, right? And now we want the number of outcomes that do not include purple. Well, that's just our total minus how many do include purple, right? And that gives us 2 to 8. And again, always thinking about, right, where we can check our answer, right? So if your odds, right, it's 2 to 8, and it adds up to 10, which is our total number of outcomes, which is what we want, right? So we're on the right track there. So that is the odds for including purple. Anyone have any questions, particularly on odds? Okay. So now part D says state the probability of the outcome to either have blue or green. What are the odds of this happening? So probability of the outcome to either have blue or green. Probability of blue or green. So how many outcomes have blue? Right, same, right? We have 2 here, 1 and 2. So there's 2 outcomes with blue, and there's 2 outcomes with green, 2 for every color, right? So the probability of an outcome including either blue or green would be 4 over 10. Or 0.4 or 40%. Right? And the odds of this happening, right, would be, right, blue or green, and then not blue or green. Right? So this would be 2 ways. Oh, not 2 ways. All right. Did anyone hear about a fire drill today? Okay. So quiet down. I forgot to pause the video, so yeah, I thought you're gonna have a nice long 5 minutes long pause, I guess, or just of listening to the nice sound of the fire alarm. But where were we? So we were looking at calculating odds for the probability of outcome either having blue or green. Right? So how many ways or how many outcomes have either blue or green in them? 4, right? And then there's 10 minus 4 outcomes that do not, or 4 to 6. Okay. How are we with that example? Okay. How is that example? So determining, yes. Yeah. Adjusting my paragraph. All right, so for the quiz, so again, I mentioned on Monday when I mentioned the quiz, there will be one question in terms of outcome tables or outcome trees, but it's only going to be one question. So it'll probably be similar to a question like this on page 41. Right, so something similar to this where you have two scenarios, in this case tossing a coin or spinning a spinner. You have to find the total number of possible outcomes. Right, you have to make either a tree or a table, and then you have to calculate a couple of probabilities based on the table you made. Right, so it'll be similar question to on page 41. So if I were you right now, I'd maybe star this example. Oh, yes. Let's continue. So for this example here, so Mr. Dirksen is playing a game called Sparkle. It involves him rolling a six-sided dice. How many possible outcomes are there? So for this question, I'm not too sure. To me, has anyone played the game far? Yeah, me neither. This event looks like this is only one question. I think I'm gonna skip it for now. Just says it involves him rolling a six-sided die. How many possible outcomes are there? Well, from what I can see, there's six-sided die, so there's six outcomes. But that's not a very useful example. So I don't think. I think I'll look up and then maybe come back to that example. But we'll just skip that for now and look at this one here. He has a 4-digit PIN for his credit card. How many possible combinations are there? So we have to use this info here, right? So has a 4-digit PIN for his credit card. Right, so the digits, right? So you have 0 to 9. So out of the 4, you can have one digit right? It can either be 0 or 9. And you have 10 options. It could be letters from A to Z, so that gives you 26 options. Or it could be it's also case sensitive, right? So that's 52 options because you can either have a capital A or a lowercase a. I'm going to skip this example. I'm just going to skip this whole page just because this example, it's a little more like in depth and I don't want it to get confusing for the quiz tomorrow. So I just looked on the other page. This example is a better representation of what would be on your quiz here. Right, so a phone requires a 6-digit passcode to unlock it. How many possible passcodes are possible? Right, so there's 1, 2, 3, 4, 5, 6 digits. Right, so we can think of each digit being an event. Right, so last example we had a dice and a spinner. In this example we have each digit is an event. So how many options, right? How many possible digits can be the first number for the passcode, right? Well, there's 10, right? 0, it can be either, there's 10 options. It can be either 0 or all the way up to 9, right? So there's also 10 options for the second digit, 10 options for the third, fourth, fifth, and sixth digit. Right, so our total number of outcomes, we just multiply, right? The total number of outcomes in each event. Right, so that would be 10. Right, this is just like 10 to the power of 6. So that would be, right, 100,000. Does anyone have any questions on this one? It's a little bit, it's worded a little bit differently than, oh sorry, so that should be 1 million 6 zeros. Right, so there's a million possible outcomes, or a million possible different passcodes that it could be. Right, so in this case, yeah. Sorry? Yeah. So each event is just a digit. So what is the probability that someone will guess it on the first try? how many ways? So what's the probability that someone will guess it on the first try? So how many ways can they guess it on the first try? How many possible ways can they guess it on the first try? One. Right? They have one shot to get it on the first try. So the probability that they guess it on the first try is 1 in a million. Right? Not very likely, because there's only one passcode. Right, so the odds, if I want to do the odds, it would be 1 in 999,999. If your friend saw you typing in a 2 and a 7 for the first two slots, what is the probability of your friend guessing it on the first try? Right, so now we have a 2 and a 7 there. So we know those. But this can still be any number. This can still be any number. This can still be any number, and this can still be any number. Right? So now it's essentially just the same question, but now we only have 4 digits. Right? So again, we have 10 times 10 times 10 times 10. So we want to calculate the total number of outcomes, right, of these 4 digits. We know the 2 and the 7. Right? We know that these two first numbers are 2 and a 7. So now there are 10,000 possible outcomes. Or passcodes. So now what is the probability that the friend, knowing that the first 2 digits are a 2 and a 7, what is the probability of your friend guessing it on the first try, knowing that the first two digits are a 2 and a 7? Right, well, again, the probability, the number of ways that they can guess it right on the first try, right, probability that they guess is 1 in 10,000 now. So it's a lot better. It's better odds, but not, or sorry, a better probability or a better chance of them guessing, knowing the first 2 digits, but right, it's still not great chances, but better. So do these two questions make sense in terms of what I did here? So it's a bit different because we're thinking about each digit as an event, a separate, right? We call them events. So let's say event A, B, C, D, E, and F, and each one has, right, 10 options, 10 options, 10 options. So we're using that number of possible outcomes formula. So for part D here, for some reason, you tell your friend that you only use digits 1 to 5 to create the passcode. Now you want to know what is the probability of your friend guessing the passcode on the first try. Right, so now it's 1, 2, 3, 4, 5. We still have 6 digits. But now we have 5 options for the first digit, right? 1, 2, 3, 4, 5. 5 options for the second, third, fourth, fifth, and sixth. Right, so a total number of possible outcomes right, is 5 times 5. So we plug that into our calculator here. Looking for, to the power of 6. So that gives us 15,625 possible outcomes. And now, again, we want to find the probability that we guess the passcode on the very first try, right? So the probability that we guess it on the first try, so we only get one chance, and it's 1 in 15,625. So which one's more? So now I could ask another. There could be a part E to this question. Which one is more like? Which scenario are we more likely to guess the passcode? In part B, in part C, or in part D? Sorry? Part B or C? Or part B? Part B, right? So, right, when I ask which scenario, say B, C, or D is more likely, right? We want to know which one has the higher probability. And that's the one that's more likely. Right? So if you don't, so again, if this helps, I can convert these to a decimal, right? So 0.0000001. This is 0.0001, right? And this is 1 divided by 15,625, right? 0.000064, right? Yes. Yeah. So now looking at the decimal probability, it may be a little easier to see. So part C, right, is the scenario that we're most likely to guess the password. Still not very good chances, right? 1 in 10,000, but it's the highest out of the 3. So most likely to guess, right, out of part A, part B, C, and D. Right, because it has the highest probability out of the 3 scenarios. Any questions on that one? All right, so if there's no questions, I will hand out, so in the booklet, so skip page 42 for now. But you can try. Right, so you can try up to page 46. right? So pages, I guess 43, right? There's this still small example on page 43. So 43 to 46. I want to give you some time to, I have some practice sheets that you can use as, again, more practice problems to review for your, where's my mouse here? Review for your